coverage will be up to today's lecture. So that is section 11.7. Okay. Okay, so up to now we considered periodic functions as well as functions defined on a finite cost interval, and to represent them by trigonometric Fourier series or generalized Fourier series. Okay, and also answer questions like convergence problems and the representation problem. Okay. So today we will develop a method that to represent a function defined on the whole real line. Okay, and so it will be called Fourier integral. All right. So first of all, we let f of x be an absolutely integrable complex R over real valued function, and defined on the whole real line. Alright, so this is the infinite interval from minus infinity to infinity. Okay. And we ask that which is piecewise continuous, okay, on any finite subinterval AB of the whole real line, and has the left hand derivative and the right hand derivative. At every point in the real line. Okay, so the picture, you may have like something like that. Okay, so you may have so f of x is absolute integrable. Absolute integrable means that so the integral of the absolute value of f of x over the whole real line is finite. Okay, so that means absolute integrable. So this is implies that okay, so this is implies if we limit the lower integral limit and upper limit to minus L and L respectively, then we have that. So So, which means that f(x) is absolutely integrable over L. Okay. And especially if we take the finite cosine interval to be minus L to L, then f of x is piecewise continuous. Okay, this finite cosine interval, and it has the left-hand derivative and right-hand derivative at every point in in this interval too. Okay, so especially, and so that's we let f L of x, okay, be the truncation of the original function of x on the finite closed interval minus L to L. Okay, so it's defined to be f of x minus L. And then we will define, okay, so we take here. Okay, and so this is f, the truncation. Okay, put that. Okay, the assignment of the truncation, the truncated function at x equals minus L and L to is 0 is an arbitration. Okay, it's all right. So now, by regarding f sub L of x, as in a period of a periodic function with a period 2L, right? And by theorem 11.1.2, f of x can be represented by a trigonometric Fourier series on the finite interval. From minus L to L, not including the two endpoints. And now you know the purpose for this assignment in behind is because that we want this is in one period of a periodic function. As a periodic function, with period 2L, at the both endpoint, they should have the same value. Okay, so this is the reason why I just assign value 0. I can assign value 1 or 2 arbitrarily, right? That in case that the value will be the same at x equal to minus L and at x equal to L. So that is the key point. Okay, and for our purpose, I think this is a convenient one to assign. Okay. So any questions? Okay, so overall, you can regard this truncation, this truncated function as in a period of a periodic function with period 2 pi. Okay, so as we know that so this periodic function satisfies all the premises in theorem 11.1.2, which is such as that in one period it is piecewise continuous and it has the left-hand derivative and right-hand derivative. Okay, as we assumed there. So that we have that fx plus divided by 2 okay, is equal to L0 plus summation and from 1 to infinity ln cosine n pi x divided by L plus b ln sine n pi x divided by L. Okay, for all x in this open interval. All right. And then the coefficient of the series is here, which is 1 over 2L, and the integration of f of x from minus 0 to L, and Ln x cosine n pi x divided by L dx, and the b ln x 1 over L minus L to L f of x sine n pi x divided by L for all n greater than equal to 1. Okay. Okay, so with the truncation, and from theorem 11.1.2, for every x in this finite interval, okay, that we know that the average of the left-hand limits and right-hand limits of the function f at every point x, okay, in this finite open interval can be represented by this trigonometric Fourier series, and the coefficient should be computed the following way. Okay, so we arrived here based on our study in the previous sections. Any questions? Especially if f is continuous at x in this finite intervals, then the series is equal to the function value of f at x. Okay. Now by insertion, so by inserting the formula, right, the formulas of the coefficients, A is 0, and ALN, BLN, and into, so suppose that we have this one, say 11.7.1, okay, so into this equation, okay, so we insert this back to them. So we have, okay, for any, so we fix x in minus L to L, okay. This arithmetic average, alright, it can be written here, U du, okay? So that's one, this is integral, okay. Plus, okay, when we do the substitution of this integral to here, the common factor can be moved out, Fu cosine k pi u divided by L, and du cosine k pi x L plus minus L Fu sine k pi u divided by L du sine k pi x divided by L. Okay. All right. So this just do we just do direct substitution. Okay, we'll just do the substitution. Now, we let pi divided by L, so that this becomes to be delta omega defined to be pi divided by L. Okay, so this is called the angular frequency. Okay. Right, because L has the unit time, right? 10 units, for example, second, something like that. Okay, and the pi is the gradient, so it's the measure of the angle or arc length, you can say that. So this is the angular frequency. Okay, angular frequency there. Okay, so so the combination here. So here we have 1 over 2 pi, okay, and L minus L, Fu, and the du, and the delta omega here, okay. Because we know this is L, right? So pi, this is actually pi divided by L, right? This is pi divided by L. Okay, as you can see, so we can, by this substitution, this becomes to be delta omega plus the limit n goes to infinity because the serial sum is the limit of the partial sum. Okay, and as we know that this series converges to this value, right? As we know that, so that we can have like 1 over pi summation k from 1 to n, so that this is a partial sum. Okay, and fu and the cosine. Now, pi over k is delta omega and the u. Okay, and du here, and this is cosine k delta omega x. Okay, so it's here, because pi over L is defined to be the angular frequency. Okay, plus that minus L fu sine k delta omega u du times sine k delta omega x okay, and here we have to multiply with very crowded okay. And delta omega here. This is the reason that, because in here we divide by L, right? But when we divide by, so this one becomes 1 over pi times pi divided by L is 1 over pi and delta omega. Okay. Okay. So we have that. Alright, so 1 over L can be replaced by 1 over pi times the delta omega here. Okay. Okay. All right, and we move the limits here and goes to infinity. Okay. And as we can see, because that this is 1 over pi. Okay. So we can combine. We now, if we move the limits out of the partial sum, then we have 2 times n times plus 1 integrals. Okay, we have that many integrals, and the integral has the same lower limits and the same upper limit here, and also each integral has integral with a factor which is f of u. As you can see, f of u, f of u. Okay, so you can see here. So we have f of u here. This is a common factor. All right, and 1/2 will come for the first integral here. And remember, this integral has a common factor, the angular frequency delta omega, and we have delta omega there too, right? So that you can see we should have such a delta omega. All right, so 1/2 and plus summation k from 1 to n. Okay, and now we have cosine k delta omega u, and the cosine k delta omega x. Right. So we can multiply, because this is a constant, as we have fixed the x here. So this is a constant. We can move the constant. into the integrand of the integral. Okay, so we have that. And similarly, this is a constant for a fixed x, so we can move the constant into the integrand of the integral. And so this is, we have sine k delta omega u and sine k delta omega x. Okay, together here. All right, and then we move delta omega here and the du. Okay, so now this is the integral of the integral. The whole thing is the integral of the integral over du here. Now we use the sum and difference identity for in trigonometry. Okay, so this is equal to, spatially, this is equal to cosine k omega, delta omega, and u minus x. Okay? So this is this. Yes? Before the last one? Oh, yeah. I think, yes. Thank you. Thank you. That's correct. Yes. Great. Right. So, because this is corresponding to the here. Thank you. Okay. So now we have 1 over pi minus L, f of u, and 1/2 plus summation k from 1 to n, and cosine k omega, delta omega, u minus x, and together, yes, delta omega and du. Okay, so you see it here. Okay, now we use an identity So this is the sum of cosine k theta. So you can think about that. This is equal to theta here. Okay, and k from 1 to n. So we have a sum, okay, of cosine k theta for k from 1 to n. And there is a famous identity, okay, that if we multiply with the sine theta over 2, and by applying the sum difference identity of the trigonometry, so we can have, so this is equal to sine k plus 1/2 theta minus sine k minus 1/2 theta. So you can cancel then, and this is come to 2 sine n plus 1/2 theta minus sine 1/2 theta here. Right. Okay, so now half plus summation k from 1 to n cosine k theta becomes 2. This is ratio sine n plus 1/2 theta, and 2 times sine 1/2 theta. Okay, we have that. Okay, and so that we can this summation is equal to this ratio. Okay. All right, so that fx plus f plus divided by 2 become to the limit n goes to infinity 1 over pi L minus L here, and fu, and the sine n plus 1/2, and the theta is delta, omega is the angular frequency, and the u minus x here, and here we have 2 sine half of delta omega u minus x, okay, and times delta omega and du. Now we can simplify those things. So by change of variables, okay, so the change of variable is that we let define to be a new variable we call v. Okay, we call v, so that u equal to v plus x here. Okay, now and of course the du equal to dv, because x has been fixed. Okay, has been fixed, and because of the change of variable, okay, the integration limit would become 2 minus L minus x and ln minus x here. Okay, and f of v plus x and the sine n plus 1/2 delta omega times v, and 2 sine half delta omega and the v here, okay, and delta omega and the dv. And remember, when we deduce the localization theorems in section 11.1, okay, we can replace, okay, with this ratio, especially we can replace the denominator, by, because this one actually is equal to delta omega v. Okay, it is because that when delta omega is quite small, okay, it's quite small, then the angle becomes close to 0, and so that the sine of the angle is equal to the angle. Okay, so that you can omit the sine, and 2 times 1/2 times delta omega times v is approximately equal to this quantity. Okay, and also we know that when L is very big, you can see the angular frequency omega is very small. Okay, right? So we will use the same technique, like, okay, and so we make sure that this one, we call this equation is 11.7.2. Okay, so we can show that the limit on the right. On the right hand side. Okay. Maybe because time limitation. So, all right. So, as derived in lecture note. We have that the limit sine n plus 1/2 to sine okay is equal to limit 1/pi. I forgot to put 1/pi. Sorry about that. We have this vector. Okay, 1/pi. Limit n goes to infinity. 1/pi. F v plus x. And the sine n plus 1/2 delta omega v. And here is delta omega v. Delta omega dv. All right. By the Riemann, the back. Lemma. Okay. So I will not repeat the process. Okay. But the detail, I will display lecture notes 11.7 for you. Okay, so so that this limit can be replaced by this limit. Okay, the only change is that we have replaced the denominator by this new one. Okay. Okay, and this is true. Any questions? Okay, so I just omit the derivation. Okay. So that so this is good for all x in this interval. All right, and now once once we have that, we can cancel the angular frequency here. And again, we can move V to there. All right. So we have divided by V, and the sine n plus half V dV. Okay. Now we will look at the integral, and we want to know, because if we apply, as we see that as n goes to infinity, okay, and you can see that if this is absolutely integrable over the interval, then this limit will goes to 0. But so we have to be careful. Okay, if we look at because that from L minus x to infinity, so we look at infinity here. We look at that f v plus x divided by v and the dv. All right. We have to you see that in this integration, in this integral, it's possible that 0 is in this interval between minus L minus 2 L minus x if L is very big, right? And so that we may encounter a situation that V is 0 or very close to 0, right? So that we have a blow-up situation. Okay? We have a blow-up situation. But if we evaluate the integral from L minus x to infinity, if L is big enough, so that the lower limit is greater than 0. Okay? And so you see this integral. So the integral of the f value of this ratio, as we know, this is right, because this is the smallest. So we have the upper bound. dV here, and this is equal to x okay, and this is finite. Okay, by this estimation, right, and also if we evaluate from minus L minus x to minus infinity, right? Okay. Now once again, this is L plus x minus L minus x minus infinity v plus x and dv. And once again, this is and also finite. Okay, so under the integration from L minus x to infinity, or under the integration from minus infinity to minus L minus x as L big enough. Okay, so that we have that now the same integrand right? But the integration limits are different, right? Then this is become to 0, and limit goes to infinity. V sine n plus 1/2 delta omega v dv. Also 0. Again, by the Riemann, the back-end lemma. Okay. So this shows that this arithmetic average is equal to the limit n goes to infinity 1/pi 1 minus infinity to infinity. Now we can replace the integration interval for this limited interval to unbounded interval, okay, with f of v plus x divided by v, okay, and the sine n plus 1/2 and delta omega v dv. Right here. Okay, and then n to infinity 1/pi f of u. So we again put so we let u equal to x. Okay, so we go back to, and we have u minus x divided by u minus x of du. All right. But when we look at here, when we look at this one, right? So this ratio is actually equal to the integral from 0 to n plus 1/2 delta omega, and the cosine omega u minus x and the d omega. Okay. Okay, for any fixed x in minus L to L. Okay, so that this ratio becomes to this integral. Okay, into this integral. Right, so the conclusion. So we conclude that fx minus plus divided by 2 is equal to the limit n goes to infinity 1 over pi infinity to infinity f of u integral n plus 1/2 delta omega 0 and the cosine omega and the u minus x and the d omega and the d u. So this is iterative integral, okay? It becomes to iterative integral, and we evaluate integral over omega and then over u there. Alright, so this is true for all x in. Okay. Now we want to exchange the order of integration because this is the iterative integral. The order is that we would evaluate the integral over variable omega and then over variable u. Okay. And if we want to exchange the order of integration, we need a theorem. Okay. Oh, maybe we take a break. Okay, up to 2:25. Okay. Okay, so now we state a theorem about interchanging the order of integration. So we let Rj two subintervals. Okay, properly bounded or unbounded, closed or open or half open of R. Okay, and K of xy, K of xy is a function which is defined, okay, continuous and bounded on the Cartesian product of I and J. Okay, so as we know, Cartesian product is just a pair such that consists of all the pairs such that x is the first coordinate, x is in I and y is in J. Okay, right, so K of xy is this one. And because bounded, so we write down an upper bound, capital N, okay, for some n greater than 0. Right, and the third thing is f of x g of y. So assume that f of x and f g of y are absolutely integrable over the interval I and the interval j respectively. Alright, then we have the following result. So let's state here. A for each fixed y in J, f of x, k, x, y, x absolutely. So when we fix y, then k of xy becomes to a function of x. And so the product becomes a function of x. And so this function of x is absolutely integrable. Okay, over I. Okay, and the function, so we can do integration, right? So the function f of y defined on J by the equation Fy defined is the integral over I over x k xy dx. Okay, right? Because for each y, the integrand is absolutely integrable. So this integral exists for every y. So this defines a function of y called capital F. And then this function becomes to a continuous function. It's continuous on y, on j, okay? Right. So this is very nice, right? And the second, for each fixed x in I, gy, and the k, xy. So when x is fixed, this is becoming a function y. So it becomes to absolutely integrable. Yeah. A real body function. You can say a complex, that's fine. Complex or real valued function. Okay. Just add up to write the complex or real valued function. Okay. So for fixed x, this is become a function y, and because k is bounded, right, and g of y is absolutely integrable over j. So this is absolutely integrable over j, and the function g of y, or g of x, I'm sorry, defined on I by the equation g of x defined to be j y is continuous. Okay, so it's continuous on I. Okay. All right, and then the third result C, f of x times g of x, right? So this has become to a function of x, and g of y, f of y, okay, are absolutely integrable over I and j respectively. And we have that f of x, g of x, dx, this integral is equal to g of y, f of y, dy. Okay. Okay, so that if we plug into the definition of capital G of x and capital F of y, we know this is f of x, integration G of y, k, x, y, and dy, dx. Alright, so the left-hand side is an iterative integration, but the order of integration is first doing integration over y and then over x. How about the right-hand side? reward hand is also an iterative integration. But the order of integration is first through x and then through y. Okay, and so we establish the identity, okay, of the change of order of integration. Okay, and you can see the condition, the required condition is quite mild. As you can see, that the interval I and j can be arbitrary interval, bounded, unbounded, open, closed, half-open. And the kernel, the kxy, okay, has a strong condition that it is continuous and bounded. The very important thing is bounded on the defined rectangle here. Okay, so this is a rectangle. Okay, in the plane. Okay, it's upper bound. And furthermore, we require f of x and g of y are absolutely integrable functions. Okay, so you can see that the condition is quite mild, right? And with that condition, then we have the validity of interchanging the order of integration. All right, so now we want to apply to our situation here. So we have to identify what is f, what is g, what is k. Okay, because we have the iterative integration. The I, so you can see. So now. So as an integration, this we call an application to 11.7.3. We see that I is just this interval, okay, from infinity to infinity, okay, and that j is from 0 to n plus 1/2 delta omega, okay. So you can think about that. You can think about that. This is close half open. That's fine. Okay, just set here. Okay, and the kernel. So we have u and w. Okay, the kernel. And the kernel is the cosine function of omega u minus x. Yep. So this is our kernel here. And you can see this kernel is defined, which is defined of course, right? Actually, it's defined on R times R, but fine, that's fine. Okay, continuous. Okay, and of course, continuous. This is cosine function, right? And bounded. Why? is 1, right? Because sinusoidal function is bounded by 1. Okay, bounded by 1. Okay, so we have that the kernel K is bounded by 1. And the f of u, okay, it's as we assume f u is absolutely integrable. Okay, so it's absolutely integrable over this interval already, right? By our assumption at the beginning of this section. And how about the g? What is g? G function. What is the g function here? Okay, it's 1, right? So the g omega is equal to 1, which is absolutely integrable over 0 to n plus 1/2 omega. Since we will do the integration, we have okay, so we have that. Is that okay? All right, so that's by theorem, if we can pull sample A, we have that pi f of u, right? Inside we have 0 n plus 1/2 delta omega, and 1 times cosine omega u minus x, okay, d omega, and then du, yeah, this is becoming 1 over pi, and we have 0 to n plus 1/2 delta omega, and 1 here inside f of u cosine omega u minus x, and d u and d omega. Okay. So this is our, okay. Okay. So now, so that this rho x e minus L to L, we have f of x minus plus f of x plus divided by 2 is equal to the limit and goes to infinity, right? 1 over pi 0 n plus 1/2 delta omega, and here f of u cosine omega u minus x, and d u and d omega. Now, So as n goes to infinity, the upper limit goes to infinity too. So this is go to 0. Cosine u minus x. Oh, omega u minus x, and du and d omega. Alright, and this is true. You can see this is true for any x in here. But in this representation, especially in this final representation here, as you can see, this iterative integral is independent of the capital L we select. So which means that if we make L bigger and bigger, right, then it's for every x in the real line, this must be true. So by writing L goes to infinity, we have that for all x in R, okay, the arithmetic average of the left limit and the right hand limits of the function f at each point x is equal to this integral. Okay? And you know, this is actually, as we described, this is f omega, right? As we described in here, right? In here, so the fu of the kernel here, that this is the f of omega. So note that f omega, as we know, this is the inner integral cosine omega u minus x and the du. Okay? It can be written. Alright? So by the sum and difference formula, so we have cosine omega u cosine omega x plus sine omega u sine omega x and the du. Okay, and then so we can write this cosine omega u okay, du, this one, times cosine omega x plus f of u sin omega u du and sin omega x. Okay, so we can split f of omega. Okay, so f of omega is obtained from the original function of x. Okay, we evaluate when the original function represents the kernel here, all right, and do the integration. Okay, so the omega here is just the angular frequency, right? And we have that. And so we define, so this term is deemed to be A omega, all right, because omega is the parameter here, and here this is defined to be the B omega. Oh, by the way, I forgot to put, okay, we define here, I'm sorry, I forgot to put, okay, so I find a typo error here. Okay, so now I include 1 over pi here. All right. So I have correct pi. I'm sorry, put 1 over pi here because in our integration, yeah, we have 1 over pi. So I move 1 over pi to a kernel. Okay. Okay, so here, great. All right, so that so with this definition, so we define A omega to be 1 over pi f of u cosine omega u du, and b omega defined to be 1 over pi infinity minus infinity f of u sine omega u du, which continuous. Okay, continuous 0 to infinity. Because I decided to include a 0 so that maybe as close interval. Okay, so right. This is the close interval here. Okay, so this which are continuous by an application, so you can apply of equilibrium point 7.8 parts d to a with either k u omega to be cosine omega u over k u omega equal to sine omega u divided by pi. Okay. Defined on here. Okay. And very interesting. So we have that. It is interesting. If we take omega to infinity, so if we take omega to infinity, then this integral goes to 0 by rerun the back lemma again. Why? Because f of b is absolutely equable over the whole line. Alright, so as the frequency, angular frequency goes to infinity, then this is going to 0. Okay, so A omega and B omega both go to 0 by the Riemann lemma. Okay. Okay, so this is 11 sample 4. Okay, and so then 11.74, okay, can be rewritten as here. Cosine the x plus b omega sine omega x and d omega. Very interesting. So now we can recover basically the function value at every point, basically, by using such an integral representation. Okay. Okay, so which is called, okay, it's called the Fourier integral representation. Representation of f of x. Okay, so we state the theorem here. the Fourier integral theorem. So if f of x is an absolutely integrable complex or really valid function on R, which is piecewise continuous, on any finite subinterval of R, and has the left hand derivative and the right hand derivative. Okay, at every point in R, then f of x can be represented by a Fourier integral in 11.7.5 here, this one, which this integral which is equal to f of x for all x in R except at points x is sub 0 in R, where f of x is discontinuous. Okay. Okay, there the value of the Fourier integral equals the average of the left and right hand limits of f of x at x equal to x 0. Okay, so this is the Fourier integral of theorem. So this is the main theorem in this section, and we give a rigorous proof for that. Okay, so you know how did we reach to this representation theorem? Okay. There are two cases. If f of x is an even function on R, then we look at the b omega, okay, which is f of x. So x. Now this is even function. The sign function is odd function, so the integrand is an odd function. Alright, and so the integral is 0. Okay, And so this means that in this case becomes 2. Okay? Now if f of x is an odd function, then the A omega okay. Now again, this is even, cosine is even, but f of x is odd, so the integral becomes odd, and again this is 0. So this is okay. So we can simplify the full integral representation there. Right, and so this is called the Fourier cosine integral representation. So Fourier cosine integral representation is valid for even functions. Okay, and this one is called the Fourier sine integral representation. So this is for odd functions, and this is for even functions. Okay, but if the function f is not even, no odd, then we should have the full integral representation in here. Okay. Oh, 0 to infinity, I'm sorry. Yes. Okay. Correct. 0 to infinity. Thank you. Okay, and recommended exercise, I have give you some remark on the solution of the recommended assigned homework problems. We need a theorem about differentiation, okay, under the integral sign. Okay, we need this theorem, okay, for you to use. Okay. Right. So I say again, J with two subintervals may be bounded or unbounded, open, closed, half open, interval of R. And f of x y. It's a complex real valued function defined on the rectangle I cross J and satisfying the following condition. So the following conditions. 1. For each fixed y in J, the function f an index by y defined on I by the equation. The equation says that f index y of x is equal to f of xy, so that you can say this is so-called the marginal function, okay? Marginal function. And for each such a marginal function, it's absolutely integrable, okay, over I. So for each fixed y, then the marginal function is an absolutely integral function of x on the interval I. Okay, this is the first requirement. Okay, and the second requirement, that the partial derivative with respect to y, okay, exists for each interior point xy of the rectangle. At interior point means that a point not on the boundary, okay, not on the boundary. Okay, so that's the interior point. So the partial derivative of f of xy with respect to y exists. Okay, and there is a negative function g of x, which is absolutely integrable, okay, which is integrable over I, okay, such that the partial derivative of f of xy with respect to y is upper bounded by g of x, okay, for all interior point of, okay, alright, so we have three conditions for f of y to meet, right? So we have to check these three conditions, right? Then for each given y in J, okay, the partial derivative, right, of f of y with respect to y is absolutely integrable, okay, over I. And the function f of y defined by the following integral Okay? This integral always exceeds y, because from the first point, first condition, that indexed by y, fixed by y, this function is absolutely integrable over I. Okay? So this integral always exists. Okay? This is from the first condition. Okay? So now we have defined a function y. And this function y is differentiable. Okay? It's each interior point of J. Okay, so y is in J. Okay. With the derivative given by the formula here, so that the derivative, okay? So the derivative, okay? So the derivative of y is given by dx. Okay? Because we say that this partial derivative is absolutely integrable over I. Okay? Well, okay, for given y. So if we can say maybe it's better to, okay, so the partial derivative here. And why is that? This is the derivative d of dy, and it's I f of xy and dx. Right, so if we want to do the differentiation of this integral, okay, then we can do that. We can do the differentiation first and then do the integration. So basically, we can exchange the order of differentiation and integration. So this is called the differentiation under integral sign. Okay, we can do so. But when we do the differentiation first, we have to do the partial derivatives here. Because f of xy is a function with two variables. These are sufficient conditions. Yeah, you may have other sufficient conditions, but this is one of the version of differentiation under integral sign. Okay, I pick up a version which is suitable for our applications. Yeah. So you can see my remark in my recommended exercise that I ask you to use this theorem to solve some of the problems. Okay, so I stop here. Okay, and I think I believe you have received the lecture notes on section 11.6 already. Right? So I will soon distribute the other lecture notes to you. Okay. All right. So we will have we have quiz next Monday, and the first meeting is examination next Thursday. Okay, right, and the coverage up to today, so it's up to 11.7.